Today we're going to see a very interesting topic. When we have the transfer functions and we have the numerator and the denominator, what does it mean to change those coefficients on the denominator? That's the subject of today. So those coefficients have to do with the roots of the characteristic equation, and we would like to explore how changing those affects the system. But before we do that, I will give you a presentation about the different test signals and the kind of tests that we do on systems. We are seeing one on the screen right now, which is a very interesting one. You have in here the case of a space telescope, and then you have the space telescope pointing control system. In other words, if you have a telescope like the Hubble, for example, and you want to be able to point this to the right star or wherever, so you're gonna need some sort of a control system that acts intelligently and tells you where you should point out. So you have this tracking and data relay satellite system that is helping you to communicate with the ground. But you see, the model is it boils to this. This is your process, which is the device you're trying to control. There is obviously some measurement that takes place. You have the input is the position of the star you want, and this is where it's actually pointing. So if you compare the pointing to the position that you know the star is at, the difference between these two will produce an error. That error will go into the controller system that will modify the attitude and orientation of your process. That's the idea here in a nutshell. At this point, however, we want to concentrate on here, and just as announced, before this controller acts, we need to know how changing the coefficients of a transfer function would actually translate in different reactions of the system, and we want to learn those. Okay, let's take a look at the signals here that we use to test systems. On the left hand side, we have a step input signal that you have in here. This is the step input in here. You can also use a ramp function, or you could use this quadratic. So these are test signals that we have. In here, for example, if you have the system here as a transfer function block, your input is over here, this is the output. Yeah. What we have in here, as you see, is called a closed loop control system. So what we have in the is in here in block diagram representation is the open loop control system. If you have a second order system, let's say in the form of this transfer function, you could actually feed back the output, compare it with the input, and then any correction will need to be done on the system. If you have several damping regions, for example here, you have a situation where this is the damping ratio, and what you need is to study the changes of this on the response of the system. And that's what I want to show you next. Seeing here, you can see that if you have um, a damping ratio of 0.1, for example, here, this is the oscillation when you have a damping ratio of 0.1. If you have a damping ratio of 0.2, you follow the blue line. Damping ratio for 3. All right. Okay. So if you can see in here, the damping ratio in this case is 0.2, 0.4, 0.7, and 1. So with 0.1, you get these oscillations that the black line tells us. With 0.2, you get less, 0.7 less, until the system is has no damping. So what we need to do is to be able to interpret these graphs as we get the simulation, and that's why we need to look at this topic. Here's a closer look of this idea that omega, we have a clear idea that with the blue line is with the damping ratio of 0.1, we with 0.5, with and with 1, you see there's no, the oscillations are disappearing. This picture you must know, and know it by heart. This you must know in your mind. You see in here you have this is the response, this blue one. It has so many technical words that we need to know. For example, if you put a step input, there's the dotted line. If the output goes past the input, like in this case, the output is going to read this instead of staying over here. If you do this, then the distance between the response of that is equal to the input and the top is called the overshoot. This pointing here, the time is called peak time. But you see the system is going to tend to die down or to stabilize at least and not oscillate anymore. What do you think happens here? From the pictures that you see in there, what can you conclude?
Reach a steady state at that point.
Very nice. And what can we talk about the steady state? On this picture, anybody notices something?
Is it offset with target value?
Is what?
Is it offset with target value?
No, not this one. And this one, what's important are the basic concepts. You see, this is the rise time, the overshoot, um, you have another oscillation or two, and then you you stay like that. So what does it mean? You say steady state error here. It means that the blue line would never track the dotted line, and therefore it is the steady state error. Now there are ways to modify that and to make it better, but I think DIA reveals that there's going to be a steady state error. This is important to show you something a little different in here. If I can point out to the fact that the signal here, you see it has oscillations where the natural frequency of this is 1 radian per second. And nevertheless, this thing goes to the end here and dies down, right? But look at this guy. The response is very fast. And also it has that peak value here, but the frequency is very different. So what does that tell us? That systems can react slowly. For example, like the black one. If you are dealing with a chemical plant, many of the processes do not involve short times, involve days. So for a chemical plant to have a reaction on a couple of days on one cycle may not be may not be bad. It means things are working okay. But if you're designing a fighter plane or some other device that requires speed, then you're gonna get plots like this. Okay, but the lesson to learn from this picture is that for slow processes there is all this we cannot expect a lot of oscillation, though it may take a long time. But for fast systems, we have the the blue line, so you can see that it will be 4 times as faster, 4 times or more faster than the system represented in blue. However, if we increase the damping ratio to the point that is overdamped, you will not see any oscillations. In this case, psi with 0.7 actually is doing is testing the system with 0.7 as well as as 1. Okay. I mentioned to you about the location of the roots and what do they mean. What you have in here is an example of a set of roots, Lewis common conjugate pairs. So this is like a close-up system. All right, but and here's where those roots would be. Now we can look at what other areas the graph encompasses, but for now I think it's sufficient to say that you have these natural frequencies. Okay. So we need to see by the location of those roots what happens. And this is what happens. You need to know this also in your mind. What happens is that if the roots are on the axis, depending on how high the frequency also would change. And see, this looks very different. And then one conclusion we can reach very easily is that if we have roots on the right hand side, instead of dumping out, they're growing up. What does that tell you? Never have roots on the right hand side. That's one message that I want to convey to you. So we might go up to the imaginary axis. This would be the limit about which the system either on this side is unstable or on this side is totally stable. But now we need to begin, now that we have looked at the system and we have done several models, it's time to build a process like a controller can modify. Like in this case, the process is this big block here. And then you have the controller here. So this is what we study in this class, and I would like to take a peek at the reaction of some systems based on the value of the coefficients. Okay, let's do that now. So in order to do that, I would like to get an example of a transfer function and have you realize what the response is going to be. We're going to try with the step input in here. So let's say that we look at an example that I had in here. Okay, this is the transfer function in here with some numbers. And what we're going to do is I am going to call MATLAB, and I will enter this transfer function in it, and then I will see and do some tests. So let's just go to where MATLAB is, right here. Okay, so right here. Yeah, we just want to run it. Okay, this is my MATLAB prompt. So what I'm going to do is I'll put this transfer function in. Let's see if we can have these two together. Maybe. Yes. Okay, so in here I'm going to say the numerator is equal to so we'll put the number in here 200. Know that because it has the value in there. I'm going to put the denominator. This is, yeah, the denominator would be 1, and then there would be a 10 and a 200. So now that we have done that, we define the new transfer function as being transfer function. So do you see now we have the transfer function on the MATLAB exactly as the one that we proposed. All right. So now what I would like to suggest is that because this is a second order system and it has some damping here, that we change this value and see what the system does. Okay, so I think I'm going to say step and then put the name of that and see what the system does. Pretty nice, huh? This is a nice graphics for MATLAB. Here, let me make it big. Very similar to the one that I showed you with the previous slide, but this one does not have a steady state error, or at least very, very little. Yeah. But this is what we would judge the system on if we are designing it to see how it reacts. So this is the MATLAB output. So what we're going to do is we're going to change that number. See that number 10? I am going to change this to 50. More damping, very much overdamped system. And okay, so we got that plug. We're gonna change the, I'm gonna say 10 instead of 50. We're gonna reduce it to 10. No, 10 we have. Let's say it goes to twice, yeah? One is, no, this is 2. 2, and then 1, and then 200. Okay, let's plot down this, step this. Oh, we needed to transform the into a transfer function. There it is with 1. And here we do the test. See? What a difference, huh? And I'm just gonna try to change the another one, and instead of going down, I'm going to go up. From 10, I am going to define it as not like 1 like last time, but 50. So the system is highly damped. And then we will have the conversion that we have in this case. So we have this. Okay, what do we have in here? So we change that, and we are back in here. We're gonna change this instead of 1. I think we put 50. I think we did the 50, but let me try this. Yeah, this is 50 right now. So a lot of damping, but what would happen if instead of 50, the number is 0? I'll say, so I need to look for then. Mhm. Yeah, this is what we're gonna do. I'm gonna eliminate the damping. So this is 0. And watch what happens. What should I expect to see based on what I have told you before about this? There is the transfer function, and now we will have to do the plots step. Guess what happened now? See it here? Because we took the damping completely out. So, conclusion. The coefficients of the characteristic equation have tremendous influence in how the system responds. And I am here to tell you that the roots of that denominator called the characteristic equation, these roots can tell us also a lot about how the system is going to react. I'll show you the slides where I had it on the right hand side. It will be unstable, but on the left hand side of the imaginary plane and the imaginary axis, it's okay. But so here we did 3 tests, one with medium damping, one with high damping, and one with no damping, which is this one.